Yeah, right? Oh, I like it when that happens. No, I've been looking forward, like, when I first found out about this conference, I saw some of the video online, and this walk-up music. I'm like, oh, I want to do that. I didn't even have a talk yet. I'm like, I'm trying to pick out music. What am I going to do? All right, well, good morning. I'm Monta from FoxGuard Solutions. And we're going to talk a little bit about jumping air gaps. So, where do we start? Let's start here. What is an air gap? Well, maybe that's fairly easy. That's where we're going to try to isolate part of air industrial control system equipment from a real network as part of protection. We don't want to have any kind of wired or wireless network connecting this thing. That's part of air protection. And what's the interesting part about these kind of connections is that we start to see for sophisticated industrial control system attacks, it's not let's just do something and see what happens. If we trip our plant, that used to be a thing. Now that's not that interesting, right? Reed, who helped do part of the Trisus, Triton, Hatman reversing, he called it needs another name, he called it Sucksnet. Because they failed. They only tripped the plant, right? They didn't get to actually do any real damage. So significant damage in your plant needs a lot of reconnaissance, needs a two-way communications channel, a persistent communications channel. So that's part of what we want to look at. So I began exploring jumping air gaps. How hard can this be? How interesting can it be? And I started with this. So this is a little microcontroller. It's about $20. Yes, that's hot glue. And a cadmium sulfide cell. This device, I literally just plug this cadmium sulfide cell directly into this microcontroller. It's a light sensor. And so I can hold it over this caps lock light and exfiltrate data. So I wrote code and created the hardware and wrote the code to decode this data. A friend of mine, another Reed, not that Reed, wrote the software to modulate this caps lock light. So you can blink these lights so fast that you can't see them and use that as a communications channel. So is your DLP, your data loss prevention software, looking for data going over the caps lock light? Probably not. Your IDS? Yeah, maybe not. Your span port, right? So these are other communications channels, and they're really not that hard. And I'll tell you what, if you folks want to, we'll pass some of these around. This is, it's random hardware, but you ready to catch? And when you get through, if you'll just put it back at the table back there, I would appreciate it. It's a little hot glue and whatever. So if I could do it, look, it's really not that hard to do. Oh, one of the things that we found out is you can modulate these lights so quickly that you can't see them flash and extract data. One of the problems here was they were already modulating this light. Any guesses why they were already doing a pulse width modulation on this light? Brightness. Yeah, they want to control how bright this light is, and that's a pretty standard way. So we had to modulate on top of the modulation that was already there. But this isn't new technology. We've been doing this forever. Anybody know what that is? What? No? Come on, be loud. I need you all. I didn't want to do all this by myself. Anybody have one of these? This is a Microsoft watch from the 90s. No, it's before Zune. Better than Zune. This is your PDA on a watch. Now, this was before USB was invented. How do you get data into this thing? With this light sensor. And I bought one of them on eBay the other day. So you hold it up to your CRT. It doesn't work with the modern displays, LCD. You hold it up to your CRT and it flashes. And that's the way you get data into this watch. Right? Mid-90s. So we've been doing this stuff for a long time. It's not new. Maybe the applications are newish. But not particularly new. And what's this? Who knows what this is? Well, speak up. Don't just wave your hand. It's a modem. It's a dial-up modem. And typically on the front of these, you have little lights that say TX and RX. What does that stand for? Transmit and receive. And in the early days, you would connect them directly to the transmit and receive lines. So guess what happens? They blink the data off those lights. The NSA figured this out in the 60s. If you could see this modem through a window and point a telescope at it, you can decode the data coming off the communications channel just by looking at the exterior lights. They blink very rapidly. It's pretty cool. But we've been doing this for a long time. Now, ultrasonic. So I built this device. This is a $5 cheap Arduino with a little piezoelectric speaker. And I can send sound, I'm sending in the 18 kilohertz or so. I can't hear it. Maybe some of the kids can. But it's sound that you can't hear, right? And I can modulate that the same way and transmit data. So I created modulation, created the device. I'm sending out data. My friend, again, wrote the Android app. We wrote an Android app to decode text so that we could send it. It's not particularly difficult. I don't think I'll actually pass this around just because there's still wires hanging off of it. Not particularly difficult. As a matter of fact, though, I can do this with basically anything that has a speaker and probably just about anything that moves. Patrick mentioned playing with drill before, right? You can make it. But if you have some kind of actuator, generally you can modulate those and modulate and get sound off of it. With this device, I can send data probably about across this room fairly easily, fairly well, and pick it up with a cell phone. So now you have a connection, from a device. Now we need some special hardware. All right, the first one, I needed the special hardware we're passing around to decode this data. And here, well, we need hardware in terms of a cell phone and the cell phone app. But we've been doing this forever as well. Who knows what this is? It's a remote control for a television from like the 50s. They call them clickers. Any idea why? Right, that's what I always wondered, right? You call these things a clicker? Well, this is where this came from. Here, we'll send this around going this way. Again, if y'all just put them in the back if you want to play with it. So, technology that's old as forever. I'll ask, how many transistors are in this thing? Any guesses? None. Yes. How many capacitors, resistors? None. How many batteries? None. How does it work? What? Okay. If you look in the end, you'll see tuned aluminum rods. And when you push the button, basically a hammer smacks them, right? And they're tuned to different frequencies that you can decode. So we've been doing this. We've been doing ultrasonics forever as well. What if I want to send stuff by radio? Radio transmission is actually very easy. Anytime, any place, I can toggle a data line on or off. I can create a small radio frequency. In this case, another Arduino. They're cheap, they're easy. If you notice this theme, it's me working on the cheap. If anybody wants to sponsor a big lab, talk to me after. It's doing this stuff on the cheap. But anytime I can blink a light, control a signal, a data pin somewhere, I can generate a very small radio frequency signal. So this just has an LED. This just has an LED on the end of it, which I like because it also gives me some wire. And generally, the more wire I have, the better my transmitter is. But now, to receive that, to be able to get the data off of that, and I modulate this one in Morse code, you need some specialized hardware. Nowadays, that's an SDR radio, $20-ish more or less from Amazon delivered, and the output might look something like this on a computer. So it's not very difficult. The range, again, maybe half the distance of this room. It sort of depends on how much voltage you have and what your antenna is like. In this case, not very well. But we've been doing this for a long time. Matter of fact, I've set this up now as part of a cyber range. This is one of the capture the flag challenges, is we'll be sending some passwords from a little Arduino like this and asking people to try to recover them. But we've been doing this forever too. Who knows what these things are? Who knows what that is? Did somebody say computer? Oh, okay. Anybody else? Blockchain in the cloud. Last time I did that, somebody had a blockchain in the cloud talk right after me. I felt so bad. PDP, PDP-8, right? These were industrial control systems in the 60s, right? If you ran an industrial control system, you actually just a couple of years ago, I saw a big company that I will not name, GE, advertise for a PDP-11 programmer like 2 years ago. They had some robot arm that they still needed to control in some nuclear facility. Anyway, right, you program them off the switches. That's beside the point. The point is that back in the 60s, we figured out that you could write software on these with loops of different frequencies, and with specialized hardware, an AM radio, you could pick up simple tones, simple tunes. You could play simple music. So that's nothing particularly new. This one is interesting. This one is a little newer. This is implanted hardware. Oh, what is this thing? What does it look like anyway? A USB cable, a USB data cable, which is very cool. Excuse me? Yeah, it does. This is where you put the SIM card. It is right in the front. So it sends voice and GPS location, so it claims. You put the SIM card in the front, you pull this little thing off. We'll pass these around too. I get that back. So they say it sends voice and GPS. They don't say anything about the data off. That probably goes straight back to China. Well, if it makes it back to the back, we'll give it to Marcin and see if he can do some wireless man in the middle and see if it does anything on that. This one's even more interesting. Anybody know what this is? Yeah, it's the thing. That's its official name, the thing. This thing, which is a wooden carving of the U.S. seal, right, was given by a group of Russian school children to the American ambassador there in 1945. And he took this plaque and he hung it up behind his desk. We know where this is going. It stayed there for 7 years and through 3 ambassadors. And then somebody figured out that it's a completely passive way to sniff information, voice, out of the environment. No batteries, no electronics. It's basically a resonant cavity. And if you light it up with the right microwave frequency, it will remodulate that and you can pick that up. Right? Matter of fact, depending on the way buildings are built, those things might exist naturally in steel. And I wouldn't be surprised if we saw people trying to light up buildings with microwave just looking for audio. You know, we don't know. Maybe that's what's going on when we hear about stories like Cuba or elsewhere. But this is a pretty amazing device. In 1945, another piece of trivia, anybody know who helped build this thing? Anybody recognize the name Leon Theremin? Theremin? That theremin, you know, with the little wah kind of radio music thing. Yeah, I didn't know he did like real work. I thought he was an artist. Yeah, my girlfriend's going to get me for that one. But a lot of times we find out that air gaps are impractical things, is that we really need some type of communication outside air network as well. Whether it's vendor maintenance, tuning, or back to the business unit to provide some information about what's going on inside the plant. So air gap is impractical, and that's where we might come up with looking for a better solution. Now, if you were an intelligence agency, you might want to run this like this, where you would like to be able to get data from the internet to inside your facility and keep it, and keep any data from the inside to going out. Right? Pretty typical application. In industrial control systems, it's the reverse. Right? We want perhaps data to go out of our plants. What's the performance look like? How much of this product are we making? How many kilowatt hours and so forth. But we don't want anybody to be able to send signals back in, like control signals. So therefore, we need something like a data diode. This is based upon the concept of a diode from how many electrical engineers or electrical hobbyists? Yeah, okay, so a quarter or so, right? You know, a diode only will allow current to go in a single direction. We want that to happen for data. And so we end up with a patent from 1997 about how this works in the real world. All right, so I want to walk you through this for just a minute because it's a fascinating concept, is that we want data to be able to go in this direction, right, from this device over to this device and not the reverse. And crudely, the way this happens is that on this side, there's a flashlight, and on this side, there's a solar cell. We have flashlight, we have solar cell. So now we can blink a light, and we can detect that light, and we can turn it into data again. So now our data can go from here to here through this flashlight and the solar cell. But data can't go the other direction. We can't make the solar cell emit light, and we can't make this flashlight receive it. We're protected that way by physics, right? The physics say that with this connection channel, we can only go in a single direction. That's pretty cool. Kind of like this for people, right? This is your unidirectional gateway. Now, I'll use these terms interchangeably. They're slightly different. If you want to talk about the differences, catch me afterwards. But, right, people can walk through this in one direction, but to go the other way, you need a Star Trek transporter, right? This just doesn't work. You can only go through this in one direction. We call these data diodes unhackable. That's a pretty good term. What do we mean by unhackable? Let's think about, for instance, what if we were using a firewall? We have this firewall in between these two segments. Now, imagine I was able to put malware on this firewall. Right? You have to give me, for the purpose of this discussion, that we can get malware into a place one way or the other. We see that over and over again, whether we have vendors or employees or phishing. What we're interested in is a persistent connection to do the most damage or to prepare to do damage. We want a persistent connection. So imagine this firewall, and you've given me that I can get malware on it. Not a big stretch, just a little one. Can I modify this firewall so that we can now send data in both directions? Yes, that's what they do. If I can modify the configs or I can modify the software, now I can send data in both directions. But what about this data diode, this unidirectional gateway? If I can modify the software on both sides, we can still only send data in a single direction, right? It's enforced by the physics of this connection on the inside. So that's what we mean by unhackable. See, another patent a little later on, I think this is from 2017, where the center of this data diode is created using an optoisolator. And this optoisolator has a light, literally a light generator and a light detector built into a single small IC. It's coated in a dark epoxy, so no light can get out or no light can get in. And that's the implementation. So I built a model of this version of a data diode. One of the reasons being is that my boss didn't want to give me a couple $100,000 to try to break these things. I don't know why. I'm sure I can break them. I just don't know if I could do it usefully. So this is my implementation. So in our unidirectional gateway, a little bit of its magic is that we have a computer on both sides so that we can pretend to run TCP, a full duplex connection on this side, and pretend to run a full duplex connection on this side, but really in the middle we only get this unidirectional form. So I have 2 microcontrollers here. This is the microcontroller inside my plant. That's the microcontroller outside my plant. And in the middle is this opto-isolator. There is the little light emitter and the light detector. That's electrically isolated. It's completely separated, right? So we've got communication going up to it. Then we're using this unidirectional data diode property of this opto-isolator to send data to this side. Also, to make it a little more graphical, the implementation has a balance of plant. That's this sort of power supply, this cooling fan over here. And inside the red line represents the data diode. This represents a plant. This represents outside the plant, where we're going to send some data. We're going to send coolant flow or temperature or widgets created or power created or some kind of data outside of the plant using the setup. And you have to have a big red blinky light. So in this case, the light's green when everything is going well, and the light turns red when it goes badly. I know some places use red when it's working well and green, right? Who uses the red when it's working well in your plant? Yeah, right, we have some electrical people. But in this case, I like green for working well. And let's walk through a quick demo of what this device is like. So we have this cooling fan running, and we're generating some data on the inside of this plant. That's me turning that knob. And if you notice, this number is changing. Data is supposed to go out of my plant. That's the way this thing is supposed to work. So that's the demonstration. Our light's green. Everything's happy. Maybe every day I reset the totals or something. I push this red button, I can reset the totals. I can't send data back into the plant because I have that opto-isolator in between. That's our only connection back and forth. So that's the normal operation. So now this is where things get a little different, right? Unhackable, that's a challenge. That should be fun. But this is different in that in all of the previous discussions of doing this jumping air gap, we were talking about additional hardware. We needed either an in-plant, or we needed an AM radio, or a software-defined radio, or a cell phone, or a little device with a light sensor on it, right? What I want is an attack I can email. Right? I don't want to have to send hardware. I want to be able to send this in a phishing email. So let's take a quick look at here. Fan is running. These 2 switches at the bottom represent me installing malware on both sides of the device. You have to grant me that. But we still should be protected by this data diode in the middle. Now malware is installed. And if you watch the fan, we push the button, the light comes on, and the fan stops. We're able to send data back inside the other direction. Thank you very much. All right, so I push a button, What's going on? We talked about it is relatively easy to create radio frequency transmissions. All you have to do is toggle a line, generally over short distances, and you can generate those. We've been doing that forever. What is new and what is a little novel about this attack is that using the technology inside modern microcontrollers, I'm able to create a software-defined radio that I can receive information without any specialized hardware. Without any additional hardware. It depends on having an analog to digital converter that's reasonably fast, and most computers come with those now. You want to monitor the voltage on your bus, or you want to monitor temperature, or a few things. So analog to digital converters are getting better, and they're getting faster, and they're getting more sensitive. So what I was able to do was to write a software-defined radio that could run on a very small, this little microcontroller, and receive data that was transmitted from the outside. Right? Now, I picked this particular implementation for a couple of reasons. First of all, being I know I can't transmit data very far without a specialized receiver. But this is my rule. I want to be able to send this by email. I don't want to have to install real hardware to make this work. So I know I can't send data very far. And if you were implementing a data diode like this, I know that somewhere wires have to come close together because they have to come to both sides of this opto-isolator. Now, microcontrollers and computers also allow you to do something else these days, and that's dynamically reassign the function of the pins. So before, in its normal operation, I'm sending a signal to the flashlight here, the solar cell's receiving it, and it's going to this microcontroller. When I add my malware, what I'm doing is I'm changing the function of this wire to say, this is no longer sending a voltage out. This is connected to my ADC, my analog to digital converter. This is going to be my antenna. And then on the other side, where I'm looking for a voltage input from the solar cell, I say, no, I want to toggle that wire high and low and generate the output. So this becomes possible because of additional functionality that we're starting to include in all devices along the way. As a matter of fact, it seems to me like before long, it should be possible to communicate basically only using software, using malware between any two devices over a very short distance. Because they all are starting to build in analog to digital converters, and we can do this over short distances. I could probably get about 300 bits a second coming in, and then the full bandwidth out, which is 10 megabits or whatever you're running this thing at. Somebody who was good at this could probably get a lot better, but, you know. And if we watch the whole part of the video, we can see that I can actually disconnect these wires. It's not the opto-isolator that I'm attacking directly. Matter of fact, I tried, right? It's like, oh, this thing's unhackable. It makes a perfect target. What am I going to do? I bought a bunch of different opto-isolators. I'm like, oh, if I run the voltages up really high or frequencies, can I get data through them? And then generally the answer was no. At least not with the hardware that was built into a device. Maybe if I had this very specialized hardware, but I couldn't do it. So it doesn't depend upon the opto-isolator being there. It depends on either wires on a PC board being fairly close together. Perhaps if you have wires going to switches on the outside of the case or to LEDs on the outside of the case, now I get antennas. The closer together, the better, but there's some some benefit to having longer antennas a little bit. The frequencies I'm using is actually a really low frequency. Matter of fact, it's a it's a COM port speed, 57,600? Is that the higher speed? Anyway, I picked that as my transmission frequency for a couple of reasons. Number one, I need a fairly low frequency to be able to receive through this analog to digital converter. And I had in the back of my head later on is that maybe if I wanted other transmitters in a facility, I tried switching lines high and low with ladder logic on PLCs, and the frequency I can switch those at is fairly slow. So if I want a higher frequency, I would probably consider at least trying to look at serial ports. Maybe I can generate faster frequencies there. So that's what I chose for a low frequency. All right, so for the record, this isn't a break or vulnerability in any particular product. This is an example of perhaps new tradecraft or new reasons for exploration into these possibilities. Proof of concept. Now, generally, your data diode should have some nice RF shielding around it, right? You want to protect. We're thinking about, oh, will data leak out of this device, right? Tempest kind of stuff. Can we pick it up externally? In this particular application, though, that's a good thing, because that RF shielding works in both directions. It keeps it nice and quiet inside the box, making it easier for me to distinguish my signal from noise. So that works both ways. Potential to use generic hardware as a receiver. I think, like I said, we will probably see more of this in the future because all of these microcontrollers and computers now are coming with faster and faster analog to digital converters. It's not that special of a hardware kind of thing anymore. So what used to be perhaps impossible becomes possible because of additional functionality of the hardware that maybe you didn't want. You just bought this device and it had additional functionality. So the other final sort of mitigation is that if you're going to do this, there are multiple types of implementations of data diodes. Right now, my recommendation would be make sure you get one that are in 2 boxes, separated by fiber, probably, at least a yard or 2 or 3, right? That's my transmission distances right now. I haven't really tried to see how far they go, but they're probably on the order of, a dozen centimeters or a few inches, somewhere along that line. So we want to really get some distance between them to mitigate this particular type of attack. And yeah, I was running completely independent power supplies and so forth in the example. So finally, our wrap up here. Air gaps. I go into a plant and I talk to somebody and they're like, yeah, we have an air gap. I'm like, really? You do? How do you get your data back out to your business unit? Oh, well, that comes in through this firewall over here where I'm like, what? I'm like, what do you do for like if you have a problem and you need maintenance? How does this vendor get in? Oh, we have this modem, right? We've got this cable modem or we got this cellular modem. I'm like, what? Air gap. You keep using this word, air gap. I don't think it means what you think it means. What do you think is the largest air gap to some manned facility? All right, I started to think about this. Oh, the International Space Station. That's a good one, right? There we have a real air gap, all right? There's no air. Not bad. Do you know they've been infected by a virus? Twice? Right? So that's about as good an air gap as you get. What I don't want you to do is I don't want you to go back and say, Monte says that we should not use data diodes. No, they're great. They're fantastic. But I want you to understand that nothing is perfect. There may be vulnerabilities. Also, depending on your particular implementation. And you have to be a fairly mature security organization to use them. If you have a network that has 11 connections in and out, and you add a data diode to it, now what do you have? You have 11 connections in and 12 out, right? That doesn't help you at all. So you need to be a relatively mature organization to use them, but they're still useful. And finally, none of security practices are perfect, but we do them anyway. But the real takeaway here is I don't want to hear about your air gap, and I don't want to hear about your data diode. I want you to do security inside your plant. Right? Takeaway. All right, thank you very much. I'm Monta Elkins. Do we have questions coming up that I will try to answer?
Thank you very much. Very interesting to see all your hacks.
Hang on. See if I can do this the right way.
Small gift of appreciation. There you go. Thank you very much. There are some questions for you.
Sure.
Are you ready?
I'm ready.
Yeah.
As I'll ever be.
Okay. Would it work if we pulled up wires from side opposite antenna wires?
Well, so in general, length is your friend, although at the frequencies I'm using now, these wavelengths are really long, like so long that it's hard to get a reasonable fraction of that as an antenna. I suspect I keep seeing the speeds of analog to digital converters increase, and that means I'm able to use higher and higher frequency. So I think over the next few years, length of the antenna will be even less important because I'll have PC board traces that are reasonable microwave lengths, and that should be able to increase my distances.
So here's another one. Aren't air gaps dead anyway? I think that you answered that more or less.
Are air gaps dead anyway? You know, that's like, I wasn't really going to tell people this, but that's the real point of this talk, is I don't want to have a discussion about your air gap anymore. I'm tired of that, right? So let's just pretend that even if you had one, it's not necessarily all that you need. You have employees, you have vendors. If we can get multiple viruses on the space station, if you can get them in the TANs, you can get viruses.
Yes. Good answer. Does it make sense to implement Tempest hardware for critical components in the ICS SCADA network?
You know, this is an interesting question. I think in general, do we want all of our hardware to be Tempest? Oh, man. And I see some of these discussions about, what about our sensor kinds of devices? What's this mean? Money, time, and trouble. Yeah, it's money, and it's time, and it's people, and it's all those things. Look, first, no. You need to secure your HMI, right? My other computer is your HMI. You need to secure your HMIs first, right? You need to secure your network. Let's do the easy stuff first. Now, as you do that, you're going to push attacks into the other devices. So maybe, hopefully, 20 years from now, you'll want all your PLCs to be Tempest, if that's even possible. But right now, you're not. As a matter of fact, I say that, people say that, your next attack may come from your trusted vendor, your trusted supplier. That's a good thing. Why is that a good thing? That's a good thing because that means they're an easier target than you are. You're doing something. You're doing something right. Your level of security is improving such that we would rather attack your supplier instead of you, right? So this is something that may be, but let's think about this a little bit. I'm trying to look slightly over the horizon, not way too far down the horizon.
Yeah, excellent answer. Thank you. Last one here. What about using a malware to control the industrial process, such as slightly altering frequency of engines to exfiltrate data remotely?
Yeah, so industrial process, frequency of engines, absolutely. So, I've got 5 volts on this little microcontroller. If I have a variable frequency drive, right, and I've got 200 volts or 2,000 volts, I can probably transmit data a lot further and a lot better. Haven't specifically tried that, but the more voltage and the more power I get, absolutely, I should be able to transmit data a lot further. One of the cool things about this, people who are an implementation of a data diode into a single box or single container, or sometimes I see them on a single card that goes into a computer, is that it's physically close together. And this attack is most easily done at lower voltage where there are short distances to travel.
Okay. There was actually another one showing up in the last
All right,
second.
sure.
Yeah. What components are easiest to brick by radio or overloading?
Components are easiest to brick by radio. Wow. I haven't done a lot of work there. I mean, generically off the top of my head, microwave seems to be fairly effective, but the powers are fairly high. You can jam microwaves. So your Wi-Fi is 2.4 gigahertz. It's generally 1 watt effective power, ERP allowed. Who of you all keep 1,000-watt microwave jammers in your plants? All right? Fail, all of you, right? Because you have microwave ovens, right? You open those up, you jam pencils in the interlocks, you turn them on, now you have 1,000 watts of 2.4 gigahertz power. Microwave can do it, but it's a lot of high power, close range. Haven't done a lot of that, but you can probably microwave your passport if you want to get halted at every border.
Okay. Thank you so much.
Thank you very much.